Welcome everyone. Today we are going to discuss a polynomial regression, and this is, of course, if you haven't watched the previous two videos, which is linear regression and gradient descent, then you are going to have a hard time understanding the polynomial regression. In this lecture, we are going to discuss about nonlinear dataset and what is the difference between linear and polynomial regression, when we can use one and when we cannot, and mathematics behind it, and also we are going to program it using NumPy only, and then we will discuss the problems related to polynomial regression. So let's start. We have this nonlinear data set, right? X and Y. And what I mean by nonlinear is that the relationship between X and Y is not straight. It is linear. It changes depending on the value of X changes. All right. In linear regression, we had some sort of equation Y is equal to 2X, 4X, 5X, right? And that way the relationship remains same. But in nonlinear, relationship does not remain the same. And in real life, all our world data set is nonlinear. For example, you may see the stock pricing, you may see the in pharmacy side, we have drugs, phenytoin and also valproate, also carbamazepine. These drugs have concentration dependent kinetics. So there are systems, or there are going to be your projects which you are going to do in machine learning, where the data set is going to be nonlinear. And what happens if we use linear regression is that it cannot capture the entire relationship between X and Y, right? And you can see this is the base fit line of linear regression, and it is not capturing anything at all. Yes, of course, the error is the lowest for the linear regression here, but we cannot use this in our prediction at all when we have non-linear data set. What we want this line to bend across the data set, right? That is what we want. So that is what we call a polynomial regression, where you can see this red line is our polynomial regression fitted line, base fit line, right? And you can see it is curving depending on the data set. It has captured the X and Y relationship very well. So that is what we call a polynomial regression. Again, this is linear regression and this is polynomial regression. What we are doing, we are bending that linear line depending on your data set. So how do we do that? And that is very important. How do we do that? So let's look at here. We had this equation y is equal to mx plus c for linear equation, right? And now simply if we want to bend the line, we square or we increase the power of our independent input variable. You will understand what I mean. See, this is n is equal to 3, and here is the degree. And what the degree represent, what is going to be the highest power of your variable, right? If you have 1x, then what we do, m1 x1 x raised to 1, then m2 x raised to 2, m3 x raised to 3. If degree is 3 and one variable is there, and all of those square or all of that power has their corresponding slopes till n, right? And plus c. So what this allows us, to bend a line. Let's see, when y is equal to x, all right, then when the y is equal to only x, you can see, of course, understand that this slope, right, slope of all coefficients are, we have right now set to 1, so you can understand very clearly. So y is equal to x, then we get the straight line, right? And if we just increase the power, now you can see we got the band line. Band curve line, right? When we did y is equal to x squared, then we got the curved line. And same as we increase the degree, right? As we increase the power, our line can get curvier and curvier. And depending on your slope, the curve can change, and it can capture entire relationship between y and x. So this degree is very important. The more you increase the degree, that much complex your model gets, right? And what I mean here, see, we are in polynomial regression, we are going to sum all of them, right? We are going to combine all these three graphs into one. You can see this one, x raised to 1, 2, and 3. When we combine them, we get this new graph which captures which has captured the relationship between x and y. So right now slopes is 1, so that is why you cannot see very well. That is why the line is not curving crazy here. But I think you understood what I mean and why we square them, right? Again, we have x1 what we do if, okay, I have made another slide, I forgot about that. So this is also true in this case. You can see we have over this kind of data set, right? This is overfitting, severely overfitting, and I will explain what does overfitting means. But for now, you can see how polynomial regression can actually capture most amount of relationship between x and y data, because literally we are moving our line through the data point, right? That is what we are doing. In linear regression, we are just trying to make sure that the error is the lowest, but here we are also trying to make sure error is the lowest, but we are moving line through the data points, right? That is what we are doing. So what if you have two variables, right? X1 and X2, and let's say, and you have degree of 2, then you can see this is variable for 1. You do the same, X1, X raised to 1, X raised to 2. For same, X2 raised to 1, X2 raised to 2. And all of them have their coefficient M1, M2, M3, M4. And also we include X1 and X2 relationship. Now our model is getting more complex. Do you understand? The more features you have, that's much complex model gets, and the more degree you increase, that much complex model get. And the more complex model you have, that much it will capture the more relationship, but also there is chances of overfitting. And I will explain that in when we are going to do a code. I will explain that later words. And same, if you have three variables, then same variable 1 m1 x1 square, m2 x2 square, m3 x3 square, m3 x3 square, right? And then x1 x2, x1 x3, x2 x3. All right, and our intercept of course is there. So that is how you make a polynomial regression. All right, this is what we call interaction. Of course, there is also we add x1 square into x3 or x2. That way we can also increase the interaction as much as we want. But in general sense, the more complex you make a model, that much model is going to be only applicable to that particular training data set. This is kind of like very generalized term I am saying, very generalized sentence I am saying, but you want your model to be a simpler, not more complex, right? Because you want your model to be simpler, not more complex. Because also if you look at here, the calculation computation power is getting crazy high here, right? And if you increase, let's say you are not going to have only 3x, right? You will have multiple x, and of course your equation is not going to have only degree of 2. It may have degree of 10, or it may have degree of 8 or 12, and in that cases you really get very complex equation, right? Now, how do we find this M1? We of course need to find this all slopes, right? That is what our entire regression means. So again, we are not going to derive the equation because we already derived this equation in linear regression. We are going to use the same equation we used because we can combine all of this M into one. The only thing we need to do in polynomial regression is to modify the data set, right? What we are going to do, we are just going to modify the data set input. We are going to modify the input. So previously we had this direct matrix. In matrix we were doing directly x raised to t into y into x raised to t into x raised to minus 1, which is here, right? X raised to t means transposed. We are going to use the same equation, and if you don't know how this equation comes, we have derived in the previous videos. So you should watch if you don't want to watch entire video, then you should watch only the part where we derive the equations, okay? And this is of course using gradient descent. We are going to use the same formula that we use for linear regression. All right, let's go to the programming part here. Okay, it is hidden. That's nice. So let it just connect. This is the theory again. We have imported the pandas, numpy, and matplotlib for plotting. That is basic function we have. And here is I am creating the dataset. I am not showing you dataset right now. You will understand why. I am not showing you the equation of dataset right now. Okay, so let's run it and let's see what type of dataset we have. So as you can see, we have polynomial dataset where the line is curving, and there is of course there are noise. I have added Gaussian noise too, but you can see this is the non-linear dataset, and we cannot fit our linear regression line. What we are going to do, we are going to add polynomial regression line, right? So the only thing, we can use the same linear regression model which we used previously, which we have created previously. I'm going to use the same model. Only thing we need to do is we need to square them, or we need to make a feature depending on their degree. So let's make a code. I'm not coding with you together here. The reason is video will get very long. So let's just understand the concept. I have created this function def polarize. So what we do, we take input of x because that is what we are going to modify, a degree, and interaction is true or false, right? And of course, you can also add want to add intercept into the beta or not, but I generally don't add intercept into the beta calculation. I calculate them separately because then you have to do a lot of, then you increase the chances of error way too much if you don't understand how you are going to concat those two arrays of numpy arrays, right? So now what we are doing, you need to understand the code main. I created the new copy of x, right? Because we are going to square them. What we want, we have x1 and we have x, right? We have x data, and then what we do, we will square them, or we will do depending on the degree. So what I am checking here, the dimensions of our x, because I want to create this model, so that way we can use for multiple variable multi-target regression. We can use for one model for all. We do not need to create every time new model. All right. So we have new copy, and we took x as an array because numpy array. So if whatever case person add, if you add the pandas data frame, if you add the list, it doesn't matter. We do not get the error, right? That's why I did that. So now what I'm doing for I in range 2, we are starting from 2, the degree plus 1, right? And what I'm doing, np.append x poly, which is our new copy, into what we are adding, the whatever our new x was, right? Our new x was, we are squaring them, degree 2. If the degree is 1, then it is not going to work at all, and it will be just straight x. And if degree is 2, then 2 to 3 means 2, then it will be 2, and that way we are going to keep adding our power into our previous x. And there is this interactions. The interaction is kind of like x1, x2, x2, x3 type. And this is not entire interaction. We also need to add the squared interaction also, but I'm not adding the squared interaction. I'm just adding straight linear interaction x1, x2, x2, x3, and yeah, and x1, x3. So this is very simple. What we did, we took the shape, we took the range from the shape, and then we decided I plus 1, which is basically that, and j, right? 1, and it is going to be 2 next, right? 1 2 1 2, we will multiply that, and we will return new polarized or polynomial features dataset. So let's look at the dataset first. What type of polynomial dataset we get? So we have our x true, right? Let's just look at the data first. X true. We have our x true. Okay, what happened there? Okay, no problem. Let's say we want degree to be 2 and interactions to be yeah, there is not going to be any interaction because we do not have any other variables. Let's observe our m. Right? Okay, wait. So I should have done this before. 1 2 3 4 5. All right, this is our x. All right, and let me just polarize this. So I forgot that you will need to see how it looks like, right? See, 1 2 3 4 5, and we have squared 1 2 raised to 2 is 4, 9, 16, and 25. And if I increase the degree, right? If I increase the degree, what happens? See, right? It is 2 from 2. It is not going to do from here. It is going to do from 2, 8, 9, 27, 64, 125. The more the degree you increase, that much more it gets, right? So I hope you understood what we did there. Okay. Okay, now we are going to create our model. I'm using the exact same model we created in the previous video for multi-target regression, right? And what I did, I just added this class polarize class into here so I don't need to all time run this all time create the polynomial features of our data set. That's why I just created this class within. Though it is the same code, just I have added self, so we can call this class every time we want within the class. And I have added the MSE as a list and iteration as a list, just so we can see we can create the loss curve, right? The code is same. The only thing new I added is where it is. Yeah, I am also checking the dimensions of y. That is basic. That is not part of algorithm, but still I will explain it here. And then we are polarizing from here, right? And we are taking the input of degree and then true and epochs. That's what we have. So let's train our data set. Plotting function, yes, this is not important. You don't need to see the plotting function. So we had our data set, right? And x true and y noisy. We had two data set. So let's understand what I'm doing. Our model is MD right now. Okay, I'm very bad at namings. And I'm giving only 70. Our data set length is 100. So I'm giving only 70 here. And you will understand why I'm doing that. So let's train our model for first 100 and let's say degree is going to be 10. We don't know what's the degree of our equation of our x and y variables, right? We do not know the relationship. So let's say it's 10 and let's run it. Okay, okay, I forgot to run this. So as you can see, right, we have our model working on perfectly on training data. This is training data. We have given 70 as a 70 data set as a training, and we have kept 30 as a validation data set. And yes, of course, you cannot do like this way, but you will understand the reason why I did it. Because I also want to show you the regularization, the power of regularization. That is why I did that. So you can see it is failing miserably on the validation data set, right? It can clearly recognize the relationship in our, what can I say, in training data set, but not on the validation data set. So let's change the degree. At the 10, it is working very bad on the very bad on our training on validation data set. So let's reduce to the 7. What do we have? It is still worse, right? At the 7, it is worse. We can also modify the learning rate however we want, but I am not going into that. Let's set to the 3. Okay, 100 epochs are very low at one point, but as you can see at the 3, results is very good, right? Our model is actually working on validation data set too. Compared to the previously, results are very good. Let's say 1000, all right? 1000 is also very high, but as you can see, I haven't given the validation data set, right? Generally, how we split the training and validation data set, we make sure that it comes from every stratum, right? From here, and from here. We make sure that validation and train both data set have the points from all the stratum, but I just give only the 70, and you can see it perfectly predicted what's going to be in validation data set. But the problem comes is that when we are training, this is only 100 samples, right? And this is only the numbers and one feature. But when you are actually making machine learning projects, they get very large. You get database in the terabytes, and you cannot just rerun every time and figure out what is going to be the degree here, what should be the degree here. Let's say if you set the degree to 12, because you don't know anything about the equation, right? So let's say you set it to 12, your model is performing very bad. Your model is performing overfitting, trying to overfit, but it got very bad, right? So what do we do? How we can prevent this? Do you understand how we can prevent this? That we can just say random degree here. We can put a random degree as much as it does not get outflowed. We can say the 10, which is very high degree, right? And we do not need to worry about the degree. Our model should automatically extract the feature which are necessary, or it should understand the concept, or it should understand the relationship between x and y, that which features are required and which are not, right? So this is one way you can call it. It is overfitting. And what do you mean by overfitting? I will explain you in very simple term. Let's start our presentation. So let's say you are training a machine learning algorithm, or let's say you are training a neural network, regardless of the case, you are training to identify the cats, right? You are trying to classify the cats. It is a cat or not. And when your model is actually training properly, it only includes this. It only captures this variables. It only captures this x and y features, right? It does not capture this background noise. This is a floor and there is the grass. It does not capture them. But when it overfits, so what happens is that the entire purpose of your model becomes to recognize the given input is this exact image or not. That's what overfitting means. I hope you understand. That's what overfitting means. So if I give this two input, right, then it will say yes, this is. It will say no, this is not cat. And to be fair, this more look like Khajit than cat, but still. And it will say this is the cat. Why? Because those two pictures are exact same. That is what overfitting means. So you do not want that, right? You don't want your and in polynomial regression is very best or very good at capturing the x and y relationship, because we are literally bending our line. So it is there is very high chance that it is going to overfit on your training data, right? And that we do not want that. So what we can do that way it does not overfit on training data, and we do not need to check every time, right? So now think. Of course, we can do one way that we evaluate our model on every desired epochs. Let's say every 100 epochs we evaluate our model. Is that our model has high accuracy on the training but very less accuracy on validation dataset, then we stop it. We can do that. But or we can introduce some sort of smart way that we don't want to do that, right? Some sort of smart way. So what I am saying here, you see, this is our training dataset. The black dots are training dataset, all right, and green dots are validation dataset. So what happened here, that when we train our polynomial regression, it actually mind my drawing, but it actually fit all the training dataset, right? It is overfitting, and now it is functioning very worse on validation dataset. Okay, so what we want to have some sort of this type of line where it is not overfitting on all x data, on all training data set. So it can perform some well on the validation data set, right? You cannot get the perfect model at all, so you must understand this also. So what we are doing here, we want to include the error. That's what we are doing. We want how we can be sure that our model does not overfit on training data set. We add the error, right? We want to add error so our model performs slightly worse on training dataset, but it can perform well, or let's say not a perfect but the well on validation dataset, right? So that is the concept of adding the error here to solve that particular problem. So we had this equation, right? This is our function upon which we are doing gradient descent, and also entire calculation is based on this function, right? So what we can do, let's say first I want to ask you a question. How do we know our model is overfitting, right? How do we know mathematically? Or how do we know that our model is training at all, right? So how do we know that? You see this beta, right? This beta is responsible, or that is what we are trying to find. So it is responsible to give us the idea that either model is training or not. Why? Because beta contains all of the slopes, and that is what we are trying to find, right? If all slopes are 0, that means model is not training. But if there is a value change, that means our model is actually training. That way we know that our model is training, right? Okay. Now, how do we know that our model is overfitting or underfitting? Regardless of case, how do we know that our model is overfitting? So let's think. Once, what happened here is that if it is overfitting, that means it is using all of the x, all of the training points and all of the x features, right? If you set the degree to the 10, in overfitting, it will try to use all of those degrees, right? It will try to use all of those extra features. So that way, if we sum all of them, if we do the sum of beta, then we get the output very high. So if the sum of absolute beta is very high, that means our model is overfitting. right? And we want to introduce the error. Well, see, we cannot just add random errors, right? We want to add smart error, because then if we are adding random errors, then our model is going to perform worse on both dataset training and validation. So we want to add a smart error. So that's why. So we can see this beta, and let's say if it is very high, then we want to regularize it to little lower, right? We want to minimize this slopes value, or we want to minimize the weights. Slopes are also known as a weights, so we want to minimize the weights, right? So what I'm saying is that when we take a sum of absolute beta, absolute because there is going to be -8 and 10, or maybe -100 depending on -100 depending on your data set, but that still mean the magnitude of our beta is very high, right? When we sum them, it gives us the magnitude. And now what we can do, we can add this into this error function. Okay, so that way we can control, or that way we can add the error at the level of magnitude of beta. Okay, beta is going to change as we are going to do train, as we are going to do gradient descent, beta is going to change. So the sum is also going to change, and we will add error depending on the sum. So what I mean is this. Okay, we will include the sigma absolute beta into our cost function, the extra error, or also it is also known as penalty, adding the penalty, right? So that way we are adding the error respect to or correlated to our actual beta, right? At that moment the value of beta, but it can go very high, right? Or it can go very low. Sum of absolute can go very high or very low, and we certainly don't want to add that much. So we add one regulator, that is what we call alpha, right? We multiply it with alpha. You can set value to 0.01, 01, 10, 100, however you, depending on your data set, of course, and you need to figure out the value of alpha that way. Let's say our sum got 5, right? And you have set value of alpha to 1, then it will include 5 into your error. It will include the 5 error, right? And if your value of alpha is 0.1, then it will include 0.5. So you need to figure out the proper value of alpha. That is going to be one hyperparameter that you are going to mess with, right? And let's take a partial derivative with respect to the beta. So what do we get? The partial derivative with respect to the beta is going to be -2 divided by n, and then I am using matrix. That's why here we had y actual minus y beta x whole square. So what I am doing, transpose into y actual minus beta x. Right? That is I separate. If you haven't watched the previous video, then it is going to be hard to understand this step, how these answers are coming. But I will explain in simple terms that this is y actual minus beta x and squared. So what we did, we created the matrix that it holds all y actual, it holds all beta, it holds all x, right? x1, x2, x3, and all the values of them. So in the matrix, I can say the square to be transposed into our singular y actual minus beta x. So that way we get the answer x raised to t y minus beta x. Right, and we are adding this absolute, and gradient descent concepts are going to be useful here. I will explain in later words. So what is going to be partial derivative for absolute beta? It is going to be beta divided by absolute beta, right? Or what is going to be partial derivative or derivative of absolute x, x divided by absolute x? That means either -1 or +1, right? Answer is going to be either -1 or +1. So what we can say, it is sine beta, right? We are just taking a signature, I mean plus or minus depending on the beta, and we will regularize it using alpha, and this is our final equation for to add error in the slope, right? Into the weights. We are trying to add error into the weights. So this is our final equation for gradient descent, of course. So see, now understand what is happening. Okay, so how do we actually figure out the new value for beta if we're using gradient descent, right? We remove the partial derivative of beta and multiplied by learning rate from our actual previous beta, right? If you remember the gradient descent concept, how gradient descent finds these values, so that only then you will be able to understand what I'm doing here. Other than that, everything is going to get out of your head, right? Top of your head. So we are adding this error, right? We are adding little error into our calculated beta. We are adding little error, and we are removing that much amount of error from the previous beta. Are you able to understand? right? It is not a single value. Okay, this is going to be matrix of all of the betas, and same here, it is going to be the partial derivative beta 1, beta 2, beta 3, beta 4, like that, and it is going to add, depending on their value, we are going to add the error, right? And let's see how much change it makes. I hope you understand this. If you haven't understood what I am saying here, then you should watch previous video where we derive the equation, where we go into very detailed concept of how gradient descent works. All right. So let's go back here and let's create the new model. And of course, I have write this. If you want to read it, you can read, but I already spoke everything. So I am creating new model, all right, which is I call the class poly. What I did here is that, you see, it is called a lasso, right? Yes, I forgot to explain you that. So when we take as alpha some absolute beta, this is what we call a lasso regularization or L1 regularization. And then we have ridge regularization, where what we do, where we square the beta rather than taking the absolute, we square beta square. So what is going to be partial derivative to alpha beta, right? That is our ridge regression. I will explain that later, but right now focus on loss. So what I am doing, so I have calculated this, our partial derivative of beta. Yes, and I should have added there directly, right? Alpha into np sines self dot beta, but making it separate allows us to see allows debugging easier. All right, then we added it, and then our self dot beta is same, right? The only thing I changed is I added in partial derivative alpha into np sine dot self dot beta. Right, now let's train. This is our previous model, this is our new model with a regularization. All right, so let's train it. Let's train for 1000, right? And this is the value of alpha. Yes, I forgot to tell you that also. I modified the fit class and I have added the alpha value here. Default is 0.01. Okay, so let's start with the 0.01 and let's train. Okay, I forgot to run this also. Okay, now as you can see, they both are performing bad, right? They both are performing exact same. So let's increase the value of alpha. All right, let's add the more error. And you will understand why. You will understand why. After adding the error, it is not working at all. It is working at the same exactly as it is. So let's increase the training, right? Let's increase the training, because error is going to be, depending on the values of our alpha, error is going to be very small or it is going to be very big, right? As you can see, first one is our normal model without regularization, and you can see it has predicted some well, right, at the high epochs or high learning rate. But look here, can you see what happened there? When we increase the epochs, what I want to explain you, wait, how do we zoom? There was option, right? View output. Yeah. So what happened here is this. I will go into the in-depth analysis, but right now let's think. When we increase the value or epochs for more, or then our error is getting added, but like a small error is getting added, and it actually figure out the function without seeing it at all. Do you understand? We haven't gave this validation dataset. This our 70 dataset completes here. This is new, and our model figured out the new relationship by just adding the errors. And how did it do that? And you can see here the values of x, and that is exactly why I have put it here. You can see there is 50, right? Okay, and compare the values, right? It has reduced the unnecessary values to the 0, say 0 0.06, 0 0.08, 0 0.44, 0 0.49. Are you able to understand what happened there? Okay, let's go in-depth analysis. So in depth, I am also taking the betas, and we will see each and every beta separately. All right. So this is new function for plot graphs. It doesn't matter here. So let's train for, okay, it is 8,000, 10,000, right? 10,000, and then penalty is very high, but let's say 10. For now, 10. All right, let's understand what happens. We are looking at every beta. Okay, so let's look here. So what we are doing, the model is same. We are just looking into each and every beta, and let's see. This is our normal model, performing well on training but very bad on validation dataset. And you can see all of this MSE, all of this beta with respect to MSE. See, it is decreasing, error is decreasing, right? But none of the beta, see, it is 8, it is negative, this one is also very high, this one is 35, right? But none of the values are 0 at all. Yeah, this one, beta 7 is kind of negative, but it is not 0. Beta 7 is negative 0, so all right. This is our normal model, and look in the regularization. See, this one is the first our model, right? You can see it is going towards 0. This one is in negative. All right. This one is also going towards 0. This one is also, see, this one is beta 3 is not going towards 0. It is increasing to the 60. See, those all unnecessary features, right, are going to the 0. See, can you see that? All unnecessary features go to the 0. And the why I did not show you the equation before is this. Now let's look at our equation. Can you see? Yes. That was our equation, and in general sense what the reason what I am trying to say here is that you are not going to know the equation at all when you are going to perform on actual data set, right? So you cannot just try different values of degree. You need some sort of method which automatically filters out the unnecessary features, and that's exactly what our regularization method did. Adding a simple error solved very big problem here. I hope you understand what I mean here, right? And now let's train for more. Okay, now let's train for more. It is on 10,000, so we are generally overfitting, but that's fine. And if I give the more data set, then it will predict exactly fine. So let's increase our penalty to 15, right? And let's increase our feature here to 12 and also here to 12. What happens? Let's see what happens. Let's see what happens. Our lecture is completed, but let's just see what happens there. So when we did the features to 12, right? This is our normal model, and it actually performed very well on training, but very worse on our validation dataset. And here the same, none of the betas are 0. All features are being used, right? All of the features are being used. All of the features are being used, but here, look at here. Our model performed very well, regardless of no matter how far the actual degree is. Our actual degree is 3, or I mean our dataset degree is 3, right? Yeah, and we use 12, so it is fourfold higher than what actual our dataset need. But you can see it still figure out perfect degree. This is a very good model, all right? This is a very good model. There is very less error on validation dataset. Now you can see all of the unnecessary features are set to 0. See, this one is somewhat useful, so it is set to negative. Third one is always, this is useful, so it's got there. See, beta 4 is 0, beta 5 is 0, beta 6 is 0, beta 7, 8, 9, 10. This is, see, it is trying so hard to go there, but it just pushed back to the 0, right? And the reason why is that we are adding error regarding to the magnitude of that particular beta. But again, we are going in gradient descent, so we are using sign -1 + 1, right? So based on that, you can see it is trying to go there, but it's keep on 0. Are you able to understand why the regularization is very important? Can you see all of the unnecessary features are set to the 0 automatically? We did not need it to do anything. I can set as much as I want, and what it does, see, what regularization does is that it allows you to exclude the features which are unnecessary, and you don't know that. You don't know manually, right? Even though you are going to, that is the again, sorry, that is the different entire concept. It depends on the experience and the knowledge of data analysis or data scientists, but in general sense, you are not going to know that which features are important, which features are not, and adding regularization helps a lot. Right, now let's train it for okay, now we don't want to go any further. Lecture is over. I am just stretching the lecture, I don't know